A was 3 meters, and this is true for another. So sorry about that. I have some bad markers. There's a lot. All right, this was for rho less than 0, greater or less than or equal to A. There was 0 else. By the way, this was meant to be a straightforward problem based in part on the homework. So when you take a look at this, what I'm going to do is find out first for, this is going to be first part for rho less than or equal to A. I know that the integral of H dot dl around a closed loop has to be equal to the integral of J dot ds inside that region, and we're stipulating rho is less than A. All right, for this one, when I do the integral of H dot dl, that will come out to be 2 pi rho H phi as a function of rho, and I think everybody got that right. Is it mine or yours?
That's me.
Sorry. That's all right. You all with me on this class? On this side, what you have to do is integrate J. Well, J I gave you as 10 over rho. And it's in the AZ direction. The units would be amps per meter squared. Then I put the differential surface. And some of you know right away how this is going to go. So the differential surface is in the AZ direction, and it's rho d phi d rho. Technically, those should be prime because we're going to integrate out rho. And phi goes from 0 to 2 pi. Rho prime goes from 0 to rho. So here, I get 2 pi rho h phi is equal to, now on this side I'll take the 10 out in front, and then I end up getting, I have this rho prime and this rho prime cancel, az dot az is 1, and when I integrate from 0 to 2 pi, I get 2 pi here, and then when I integrate from 0 to rho prime, I just get rho prime evaluated from 0 to rho, or rho, and this is basically it, right? So when you end up with h of phi here, you can see the rho's cancel, the 2 pi's cancel. It's simply equal to 10 amps per meter. I do remember people put down wrong units. They had like Webers per meter squared or something.
That's the unit for B field, right?
B field is Webers per meter squared.
I'm pretty sure I put that, yeah.
Yeah, always, if you just look at the units of this, when you take a look at J, it's amps per meter squared. When you integrate a surface, it's going to get amps per meter. Amps per meter down there has to be amps per meter over there. When you go ahead and do this stuff, because the rho's cancel. And you end up with this for rho greater than 0, less than A. And then the next part, does everybody understand that part, by the way? It's a straightforward integral of h dot dl around a closed loop is just the circumference, 2 pi rho times h phi. Everything going inside that loop, penetrating it, is in the jz direction. It's just the integral of the surface density over, or the current density over the surface. So now for rho greater than A, here, again, it's always smart to put this down first. Is equal to the integral of J dot ds over the closed surface. All right, well, here, this is still 2 pi rho h phi. And over here, now, we're outside the region where the current exists, so we can only integrate the current density out to A, because there's the current density beyond that is 0. Do you all follow me, class? So here, it's going to be the same deal. You're going to have an integral from 0 to 2 pi. Now this goes from rho equals 0 to A, and it's going to be 10 over rho az dot in az, and it will be rho d phi d rho. Technically these are primed, it won't matter, they cancel, az dot az is 1. So I end up getting 2 pi, integrate rho prime from 0 to A is just going to be, this is going to be 10 times A. So you can see here now h phi itself, 2 pi's cancel, and I get h phi is equal to 10 here And then, you could, if you want to, you can multiply by 3, make it 30 over rho, 30 over rho amps per meter. You're right, I think you did put down Weber's per meter squared. I didn't take off. I'm going to try and encourage you to do the right units from here on, and I'll be clear. I'd like the correct units. Y'all with me on this one? That was the quiz. So now I'm done with that. Today I gave you though. I forgot. I didn't post that homework. Now, sometimes I forget to sync this stuff, and that's on me. But this time honestly I didn't post it. So I want to take care of at least one of these problems. We went through the force equations, right?
Yes.
We talked about, we should do at least one or two of these. Let's mention one other thing about that loop before we move on. Lower book has this. I'll tell you what page it's on in a second. This is on page 249, and I'm going to put this down here. So remember, in general, this is about torque. Symbol for torque is that it would be Newton meters, or if you think about it, it'd be inch pounds or something like that, foot pounds. If you're talking about torque in the CGS or the English units. Anyway, when we have this torque, you're used to seeing it's R cross F in the simple sense. Now, if we have a loop, and I'm just going to show you a typical kind of loop, and the loop has N turns. Let's assume they're tightly wrapped, but we have a current I and we have N turns, and the area of the loop is just pi a squared, and this is going to be the radius a. Can you all follow me? I'm trying to show you a bunch of turns, tightly wrapped, not much difference in the spacing, they're just a whole bunch. And we have a B field, and I'm going to just show you. We're going to have some B field, and assume it's uniform everywhere. And you want the torque about that loop. Well, torque about that loop is going to be equal to M that I'll get to, and it's going to be crossed in the B. Now, I think he uses B here, not H. I'm almost positive he does. Yeah, and this is equation 4.64. But I need to talk to you about M. And this, by the way, the nice thing about this one, it doesn't matter the shape of the loop. It can be rectangular, it can be ellipse, it can be circular, it won't matter. What M actually is going to be the number of turns, then it's times the current in each turn, then it's times the surface area. So far, everything's a scalar. And then there's going to be what's called a normal surface vector here. AN is just a normal surface vector. Has a length of one, or normalized surface vector. But here's how you get the direction of the normalized surface vector. Now, listen to me. Mathematically, there's a couple of ways to specify this clearly. The easiest way is use your right hand, take your index fingers and put them in the direction of the current. Your thumb will point in the normal direction. So AN is this way. Do y'all follow me? If the current's going that way. If the current was going the other way, then it would be pointing minus A. If that's the z-axis, it'd either be plus or minus AZ. Do y'all follow me on that? So that's A normal. And you can see, you can do the math on this one. Really, it's going to be this, or it's A normal cross B times a bunch of magnitudes. Do y'all follow me? That's what it is. I wanted to just get that out of the way. I don't think I did that last time, but we've done force on a piece of charge is QV cross B. We talked about the radius for a magnetic bottle. Then we talked about the force on two wires, how they pull together if the current's in the same direction or opposite directions they repel. Y'all with me? Now, at least for, did you all see that, by the way? Did you look and see that homework's posted now, I believe? It's 13 or 14, something like that.
I think so.
Do you see it?
Let me check.
Yeah,
I-
there's a 13.
Yeah, it's
No,
posted.
that's on me though. That wasn't posted. So I want to just get to at least one problem. I know you guys can probably look this through yourself, but all right, let's do problem 4.38. I need somebody to read that to me 1 second. I think most of the other problems are kind of just plug and chug. You got a charge moving at a velocity v in a B field. The force is QV cross B. If there's an electric field too, you just add QE to that and you get the total force. There's no real tricks to that one. All right, so let's try 4.38. Anybody?
Gravitational force on a mass is F equals mg.
All right, so we got a mass, right?
Yep.
And we got a force due to gravity equals mg, and we know g is 9.8 meters per second squared. All right, go ahead.
There's a line of current with, it has 2 amps of current.
2
and
amps?
100 grams mass per meter. Like,
Okay, so what we're saying is we got something, and we got, for a 1 meter section, we got 100 grams.
yes,
All right, mass equals 100 grams per meter. Go ahead. And I got a current going through it, right?
What magnitude and direction of uniform magnetic flux density would be required to levitate this line?
Oh, all right. Here's the deal. He's got a current element, right? Now look. There's a force of gravity pushing down. I'm going to assume that there's a current. How much current's flowing? 2 amps?
Yep.
Right. We got equals 2 amps. This is going to be no problem. You're going to see this in a second. 2 amps flowing through there. First, we're going to get the force of gravity. Force of gravity is what? Just mg would be pulling down. You all agree with that?
Yep.
All right, so it's equal to mass. I'll just leave it as m times g. We know it's 100 grams. By the way, for the force to be in newtons, the mass is in kilograms. So it would be 0.1 kilogram times g, which is 9.8 meters per second squared. That's the force downward, right? Now, we want to find the direction and magnitude of magnetic field, so the force, magnetic force, would be equal to it. Y'all follow me on this? So first, we want the magnetic force going up, right? We know magnetic force, if this is 1 meter long, normally it's dF. I'll just take a moment to go over here and talk about this. Normally what they say is differential force is equal to I dl cross v. Right? If we're talking about something where the force is a constant because in other words, if v doesn't change over the length, the actual force per meter would be equal to simply I times a length vector cross v. Now, y'all follow me on that? All right, come over here for a second. Let's figure out the direction. First, we know the force is IDL cross B, right? You see how IDL is going that way. Everybody follow me? Crossed in a B. To get an upper force, the B field has to be into the board. Do you agree with that?
It says the line is just from west to east, so yeah.
Y'all follow me on this?
Yep.
So it's got to go into the board. I'm just going to show you it this way. That's the B field. It's into the board. It's going to have some V naught. I don't really care at this point. And I'll say, I'll just go A, B, so it's into the board. I'll put a cross. It's going into the board. We don't know the value for you though. I hope you understand this. I'm trying to make this as simple as it needs to be. Okay, so now I equate the two forces. So I know that I, and it's per meter, so it's just I times L cross B, or just times B naught here, has to be equal to M times G. I got rid of all the cross products and everything because really, gravity's pulling it down, that magnetic force is pulling it up. Y'all with me on this? So at that, I want to make sure. Y'all see this, class? The cross products, we can do them all, but they're not necessary if you see the final effect. All right, so what is this going to be? They want the B field, right? So the B field magnitude is mg over I. Mass is in kilograms, it's 0.1 kilograms. Gravity is 9.8 meters per second squared. I is what, 2 amps? Yep. Now this would be in either Tesla or Webers per meter squared. I tend to like Webers per meter squared. Tesla's okay, but it's one of the two. So that's, what is that, 0.98 over 2. It's about a half, a little less than half. But can you tell me what that is?
It's 8.46 now.
0.46, and that'd be Webers per meter squared. What do they have in the book?
I'm not sure. I can look at the solutions. What problem is this again?
38, 438, I believe.
They have it in.
They asked for the B field, correct?
Yeah, they have it in Webers per meter
All
squared.
right, same thing as Tesla. What did they give you?
0.49. So.
What did we do wrong?
No, that's right. You just half of 9.8 is 4.9.
All right,
I think I did it in my head wrong.
Yeah.
that's not
Yeah.
4.9. 4.9. Y'all follow me? What else does he ask for that?
That's it.
That's all.
That's from.
Yeah, that's
Now,
not
most of these magnetic force problems are trivial. I mean, if you remember loops, find the magnetic moment, and just, it's really tau. I mean, it's the magnetic moment really crossed into the B field is going to be the torque about the center point. And when you have anything like that, there is no net force on it. The B field's constant. The only time you get a force, a net force, is when the B field is different on different parts of the loop. Remember the long wire where we had a current loop going around it? Because the magnetic force near the member that's vertical here is greater than the member here, you would get net motion. Y'all follow me on that, class? That's important to remember. Otherwise, you don't. One other thing, I didn't tell you guys this before. I don't think. Did I mention anything about, I'm pretty sure I didn't talk to you about this. My experience with space tethers, in other words, when you have a satellite orbiting around the Earth, they oftentimes have like cords and stuff like that that are going to be extending from. You all with me? So, the very first satellite, this, you guys are way too young to remember, but the first satellite was called Telstar. It was first communication satellite that we threw up there. And we put it up sometime, I think about 1958 to 1963, in that era, very early on in the rocketry program. So it was orbital. Now, you need communication satellites. If you want to talk to Australia or something like that, you need it's either geosynchronous or it's low Earth satellite. And you want to be able to communicate with that and have that rebeam your signal down to the shaded parts of the Earth where you don't have a direct line of communication. So this satellite was up there, and I remember this story so well. What's happening is the people that worked on this to figure out how long it would be in orbit, they only worried about the collisions with the plasma of space. It's up there. There is still some small amounts of particles, and they worried about that slowing it down. They did a calculation to take, 153 to 300 years before this thing would actually fall out of orbit. What they didn't account for is the magnetic field of the Earth inducing currents. So just, I'm not gonna show you, I mean, a satellite, whether it's round, it doesn't matter, any shape, it's got a net length, all right? That thing's going, and it's going perpendicular to the B field at a lot of points on the Earth. Now, it's a geosynchronous satellite, I think. And anyway, it's going perpendicular as it orbits. Well, that means you got a QV, or cross B, or you have an induced electric field. You all follow me on this? That electric field is causing charge to separate. Well, when charge separates, it likes to get back to where it came from. So as the charge separates, then you get an arc discharge in this very low density plasma. It's highly ionized. And you have current. Now, you know anytime you have current flowing, there is a power loss, I squared R. You with me on this? So the space surrounding that became the discharge path. The satellite became the armature, you might say. Or I should say the rotor. Anyway, it's moving. It's the thing that's motional, and it's getting a voltage, and it's discharging through the plasma space. Orders and orders of magnitude more power dissipated in there than the power loss from collisions with the plasma. And the thing just decayed really fast and ended up falling and landing in Australia. Thankfully, in the middle of an area that was unpopulated. But you know, this could have been a boondoggle if that would have hit Russia or something like that. They were trying to intentionally cause problems. Thankfully, it hit there, but that's, you can look it up. It's a very famous thing. That's what happens when you have QV cross B, or induced voltage, you might say. Talk more about that later actually in 3320, but I wanted to mention that. Now, most of these things with magnetic forces, I look at this stuff. You guys are bright. I think you can figure it all out. I'm pretty sure. But where I'm going with this is the next thing I want to talk about. I mean, I'll put those problems up there. Please just go through them sequentially. If you don't see how to do it, or for whatever reason it's not clear, let me know. It should be very clear. I mean, we can do another problem, but y'all feel okay with these magnetic force problems? It's simply applying either QV cross B, or IDL cross B, or torque cross, if you want the torque, or simply the magnetic moment crossed into the B field. And there's those three things, and that's it in a nutshell. Now, I'm going to skip the boundary conditions for now. We'll talk about that on Wednesday's class. I want to jump right into inductance. Now, inductance is something, the boundary conditions are fairly simple. H tan 1 is H tan 2, B normal 1 is B normal 2. End of story, and I'll get to that on Wednesday, but I want to talk about inductance, because this is something you've got a pretty good handle on. I think you've had laboratory work with inductance, right? You've had circuits, you've had physics when they talk about inductance. Can anybody tell me in their own words, what is inductance? I mean, you can have a lot of different definitions, but in your own words, how do you think of inductance, everyone? All right, think about it. What is an inductor? I mean, what's the first thing that comes to mind? Anyone? Well, it's a lot of coils of wire.
Coils of wire.
I mean, what you should think of, if you're an electrical engineer at least, you should think of a whole lot of coils of wire. Yeah, it's got some inductance, right? Well, that's just, it's called a lumped element representation of an actual inductor, whatever it could be. It doesn't need to have just a coil of wire. It could be a spiral of wire. It could be something where there's a contour of current that's near, that basically weaves around, and that would give you an inductance too. But what inductance is really saying there's some current path that creates magnetostatic energy in a way such that it's linked to that inductor and can be, and when you, if you want to, you can get all that energy out. That's what it comes down to. Now, we get into the real definitions. There's two types of inductance. There's self-inductance and there's mutual inductance. Have you all heard of these things?
Yes.
Okay, so first we're going to talk about self-inductance. Where's this in the book?
Inductance is on 261.
All right, we're going to talk about self-inductance. A couple of different ways to do this. One is this. Anytime you have current, and it's causing, there's a current here in an inductor, it causes a net magnetic field all around All right? Now, this is important to write this down. The magnetic energy density is symbolized as W sub m, and it's equal to 1/2 B dot H, that's the technical definition. It's also equal to 1/2 magnitude, or 1/2 mu times magnitude of the H field squared, or it's equal to 1/2, and it would be magnitude of B field squared over mu. And this is going to be in joules per meter cubed. So that's the energy density. Now I'll contrast this with electrostatics. Do you remember in electrostatics, we always talked about the capacitor there, and it had an energy density, electric static. Do you remember what that was? Anybody? Well, 1/2. And then technically it's E dot D, but it's really 1/2 times epsilon times magnitude of E squared. You all remember?
Yep.
That's in joules per meter cubed as well. That's an energy density. That's an energy density. Well, if you wanted to know one way to calculate the self-inductance, if you integrate the magnetic energy density created by that current over the volume that exists, so this is over the total volume, it would be equal to 1/2 Li squared. You'd have to calculate the current actually to cause this magnetic energy density. I'm going to get to the point in a second, but you all follow the thought on this one. And therefore, you can get the inductance. How many remember that formula for an energy and inductor? Okay. Matter of fact, let me contrast this. If you have a capacitor, capacitance C, and it has a voltage V across it, the electrostatic energy in here for a capacitor, I just call it WC here, is 1/2 CV squared. That's how much energy there would be in there in joules. And you can get that out. If you have an inductor, this is inductor energy density, right? If you have an inductor here of L and there's a current I, then the magnetic energy density is 1/2 Li squared, where L would be the self-inductance. I'm trying to just show you the parallels between capacitor and inductor's energy. Now, this is all well and good. There are a couple other different ways to do this. You can also calculate the inductance. This is really useful, self-inductance. Well, let me talk about this first. So, everybody follows me. This is called the energy method of determining inductance. Follow me on this, guys? All right, so now we get into at least one example. This is a very classic example, and the result is very classic, and it's one of those things you should know. Matter of fact, let me do it over here because I think it's really important that I showcase this. One of the things I remember in electrical and computer engineering, it's not just one little area you have to be an expert on. You have to understand lumped element modeling with certain elements. You have to understand transistors. You have to understand electromagnetics. You have to understand all the gate theory. And you have to understand Carnot mapping, JK flip-flops. You have to understand a lot of things that are, in my opinion, digital kind of stuff. It's either on or it's off, as well as a lot of physics to really be a good engineer. And the one thing I'll tell you too is, if you go out and if you look at places that employ large amounts of physicists and engineers, electrical, computer, mechanical, physicists in general have a very good handle, a good physicist, the PhD, very good handle on the fundamental physics involved with everything, from quantum all the way through electromagnetics, sound, everything. They understand physics. But if you ask them to design something like an adaptive radar, the information theory, a lot of things with signal processing, and especially with digital electronics, they don't have any real background in it. They can learn it, but I mean, it's not part of their view. When you're hired, They expect you to understand the physics very well as a lot of the technology that's necessary for implementing things. Physicists explore really nature. That's really the fundamental thing, is explaining all the interactions of particles and energies in the natural world. That's what they do. Engineers take all that information and they use it to build things, really. They solve problems that are out there that way. That's a big difference. So remember the technology part of this, all the stuff you're doing, the digitals, all the stuff. You had JK flip-flops, right? You had logic circuits. All that stuff will be very important in the real world in general, unless you're in sales. Sales are important, but I mean, there are people in sales that haven't a clue how a car works. I mean, they can sell them. They can sell them. Okay, now, let's do the classic problem. Here's what it is. We're going to have a wire of a given radius A. It's going to have a permeability mu, and we're going to assume a current I is uniformly distributed in here. All right? So now what we're going to do is calculate the H field inside the wire. All right? And we're going to find out the magnetic energy density inside the wire. We're going to get the self-inductance per meter. Do you all follow me on this, class? Now work with me on this one. This is a good problem. Most of you will appreciate how this works. So I'm saying I want the magnetic energy. First thing I need to do is get the current density. So what is the current? Let's assume this thing has an area. It's got a radius of A. It's a uniform, right? So the area is pi A squared. All right? We'll even do it. I'll do you one. I'll call this the Z direction centered on the Z axis. So we're after the amount of energy per unit meter. All right? How do I get J? All right, I've got I assumed I. How do I get J? Based on the assumption it's uniformly distributed?
I over pi r or pi a squared.
It's really I over the area that the current is penetrating, and it would be in the AZ direction, right? So that would be I over, as he said, pi A squared AZ. And this technically is amps per meter squared, right? So that's J. Everybody with me? And you understand the reasoning behind it. Now, once I do that, and here's where Ampere's law comes in. I know the integral of H dot dl is equal to I enclosed, right? With me? We just did something like this, right? This is the easy one. So now if I take this, I want to slow down. If I take this and I look right down the axis, right? And I say I'm at a distance rho, the z-axis that's coming out of the board, and I take and I say, there's my loop, it's at some radius rho, and there's the H field. So I know this, the integral of H dot dl is really going to be just 2 pi rho. 2 pi rho is the circumference or perimeter, right? Times H field. And that's equal to how much current flows through there. Well, how much current flows through there? Current density times area. Current density is constant, right? Y'all agree with that? Y'all see what I'm talking about or not? So that current density is constant. Just take the area right there, which would be pi rho squared, right? Multiply it by the current density. That would be the current closed. Do y'all agree? Now, what I did on the quiz is I made that be a function of rho, didn't I? I made the current density a function of rho. So when I do this, I say that's equal to the double integral technically of J dot ds. But from last time, you know this is really going to be this, I over pi a squared, current density, times the area of that, which is pi rho squared. Correct, class? I'm not trying to make this trivial, but I hope you understand what I'm doing. Y'all with me?
Yeah.
Okay, what happens here? Well, the pi's over here cancel, right? And when I take a look at this, I've done the integral over there, so I can take and I divide by 2 pi, and so I have h phi is equal to 1 over 2 pi rho. That's that. And then it's going to be I And here I have rho squared over a squared. So it's really going to be I, right, over 2 pi, and it's rho over a squared, and that would be h. Do you all agree with that?
Yep.
I'm going to do myself a favor. I'm going to say this is really equal to some constant k times rho, and this is for rho greater than 0, less than a, and here I'll just make k equal to I over 2 pi over a squared. That way I don't have to keep carrying all those constants around. Everybody agree with that? All right. Now, after that, next step, that's B field. I'm going to get the energy density. Y'all follow me? What's the energy density that I put down? 1/2, right? Mu times h magnitude of h squared. Correct, class?
Yep.
Take a moment. I don't mean to write too fast. Until me get out of the way of the camera. Michael Smith, who was recording the other lecture, said, sometimes I stand out in front when I make a point and I block the board. So yell at me to get out of there.
I mean, you do, but you also like say everything you write down. So I mean,
he suggested I try. Y'all with me? All right, what happens next? Now we go on to see what this is. Well, this is equal to what? 1/2 mu. What's h? H is k rho. So it's k squared, right? Rho squared. That's the energy density. Do you agree with that? And that would be in joules per meter cubed, if you want to keep track of that. Y'all with me on that? All right. Now, what do I need next? As a matter of fact, let me outline the steps. I assume from I get J. From J, I get H. From H, I get the energy density. My next step is to get the total energy, which is just going to be the integral of the energy density over the volume. And after I have that, the last step is going to be setting 1/2 Li squared equal to this capital omega M and solving for L. Y'all with me? It's similar to some of the things we do with capacitors. Remember with capacitor, you could say you get the energy density, 1/2 epsilon E squared, integrate it over the volume, and set that equal to what? 1/2 CV squared, and we could calculate C that way. Y'all remember doing that?
Could you not just do the 1/2 epsilon naught E squared?
For this problem? This is magnetic.
Yeah, but I'm saying if you, never mind.
All right, it would be mu, not epsilon. And you can get the energy density. That's what this is. 1/2 mu h squared.
Yes, sir. I was talking about so that's the magnetic energy density?
Right.
And I was talking about the electric energy.
If it was a capacitor,
Okay.
the electrostatic energy density would be 1/2 epsilon h squared. And I think I had that up there a second ago. Y'all with me? Okay, work with me now. So what I'm after next is total energy in that volume, right? I'm going to take it per meter, so assume this is 1 meter long. This is a really cool result. All right. That's the energy density. Now I need the total energy, right? That would be an integral. Technically, it's a triple integral, correct, class? Because it's a volumetric integral, right? There's my energy density. Just bear with me on this. Y'all see that? So I'm going to take, this is the energy density, which is going to be 1/2 mu k squared rho squared. And I have to integrate that over the volume. What's the differential volume in cylindrical coordinates?
Rho squared, or it'd be r squared.
Think about it. Differential volume. All right? Think about it. Now, a differential volume would be rho d phi d rho dz, right?
Yeah.
Just think about it. It's always going to be the differential. D rho would be radially. Then rho d phi is going to be azimuthally. Then dz is vertically. Not when you think about r squared.
I was thinking spherical. I was thinking spherical.
That's a common mistake. But you all follow me on this? So that's the differential volume. Now you got to put the limits on. And these are hard limits, because this is the total energy inside the radius A. Y'all with me? So here, where does rho go from? Well, I mean, where does phi go from, guys? If it's
0 to 2 pi.
That's right. And I like saying that over and over again. Where does rho go from? From 0 to radius A, right? That's my outer ridge. Y'all with me? And finally, where does Z go from? Hint, per meter.
0 to L. Or 0 to 1. Yeah.
Always make, if you got any choice in the matter, make the length 1. Wait, it's per meter without any kind of dividing by things. 0 to 1. Now that's the energy per meter, right? Let's do it. See what we get. I'm going to take all the constants out in front, so I have 1/2 mu. And then I have k squared, but you'll notice, all right, that comes out in front. Now let's do it this way. I do the d phi integral from 0 to 2 pi, I get, it's 2 pi, right. I mean, y'all with me on that? Now, I do rho, but notice I have rho cubed here, don't I? We got rho squared times rho is rho cubed. Rho cubed integrate d rho is rho to the 4th over 4, correct? From 0 to a would be a to the 4th over 4. Not done yet. Then I go dz. From 0 to 1 is 1. It's 1, thank God for 1. All right? I love those kind of intervals. So that's the energy inside here. I'm going to clean it up a bit. Y'all with me? Now, y'all see I can cancel those 2's. Just get rid of them. They go away. So I'm going to get rid of them. Now I have this, and that's equal to the actual what? It's equal to the magnetic energy, which is 1/2 Li squared. Now that would be the inductance per meter, but you all follow the train of thought here. That's what I put over here. It's the final part of the calculation, right here. Are you with me, everyone? Here's where you got to mess around and really play the game of being exact. So next, from here, if you look, I'm going to multiply both sides by 2. Y'all see that? So let's go ahead by 2. And that gets rid of that and makes this over 2. Now, I'm not quite done yet. Next, I'm going to put what k was. Well, here's what I'll do. I'll do it up here. I'm going to take this. I have Li squared is equal to, and here I have mu, I have k squared, and I have pi a squared over 2. Now, I'm going to leave it as mu, but now I'm going to replace k. That's k. If I square it, I get I squared over 2 pi squared over a to the 4th, right? Wait a second.
I think answer for this.
All right.
Oh, that's just if it's like hollow.
Then I get pi.
Did you just get mu over 2 pi?
I mean, y'all follow me right here what I'm doing?
Mm-hmm.
All right.
That's only problem. What would you pull that 1/2 Li squared?
Yeah.
That make it 2 pi then?
Well, there's the, I think you might have just forgot to bring the A4.
Well, it was A4 over 4.
So I think you might have just forgot to bring the
Yeah,
A4 over 4 and over 2.
A to the 4's gone, and it's mu, and it's over pi, so this is definitely right.
Here you mean?
Yeah, I think a to the fourth over 2 should be included in the original.
I think he's still struggling.
Oh, here, yeah.
Okay.
Yeah, you're right. Let me rewrite
Yeah,
it.
fourth over 4. That's
So
4
this is
times
going to be
4
mu
from
k
C1.
squared
That's 16. Oh,
pi
and then you multiply that by 2.
a to the
you get 8.
4th over 2. Sorry.
That's okay.
Is equal to that. Now I'm going to go ahead
Would you put
and say that really L is equal to 1 over I squared. Then I have mu I, this is going to be k squared, is I squared over 2 pi squared a to the 4th. And then I have
Those
pi
are 2. No, you're right. You're right.
a to the 4th over
No, it's because
2.
there's a 2 here.
That should be right.
There's a 2.
Oh, yeah.
All right, I'm just taking,
16.
I have a question. So that right there, where you said it's equal to Li squared, how'd you get the over 2? I thought it was over 4.
You multiplied everything by 2 to cancel.
I
out
had-
one half.
Oh.
1 half.
Okay, that's fine. That's
1 half
fine.
Li
That's fine.
squared, and I had, this is a over 4.
That works. That works.
You did this because when you integrate, it's 1/2 of this.
Yeah,
There's
yeah,
2
yeah.
pi. They cancel there.
Okay, so, all right, if I take a look at this, I'm gonna just show you. The I squareds cancel. Now, inductance, unless it's a nonlinear material, will never, ever be a function of the current intensity. If it's nonlinear, it can be, but if it's not that, if it's a linear material, in other words, mu and B, or sorry, B and H are related by mu, and mu is a constant, not a function of the H field intensity. Y'all follow me? So it'll be this. Now the I's go, and when you do this, what do you see happening? L becomes what? It's just mu over 8 pi, and that would be henries per meter. And I'll tell you what happens when we go through this. Let's see. I forgot no, that's right. One of these pi's cancels. I get 2 squared times 2. That's 4 times 2 is 8. 8 pi. 8 to the 4th go, and I have mu. That will be the internal inductance per meter. And then write this down. Just put it for DC. It is not the AC internal inductance, because something called skin effect becomes a factor. Y'all with me, class? That's the internal inductance. It's a little effort to do this because it's a pain in the butt. Now, I got to tell you something else. If you were trying to calculate the inductance per meter for an infinite wire from A to infinity, it goes to infinity per meter. And here's why. Just so you see it. And you'll see it in a second.
Wait, say that again. What did you just say?
I'm about to show it to you.
Okay.
All right, now pay attention to this, because this is one of those things that people foul these things up all the time. It's real important. If you have a current I, forget about the radius of the wire. We're outside where the wire is. Doesn't matter. So we're outside here. What's the H field at a given distance rho? H is equal to I, whatever that I is, over 2 pi rho, right? Now, what's the energy density? It's equal to 1/2, right, mu H squared, right? So it's I squared over 2 pi rho, and all this squared, right? Now, if you multiply this by a differential volume, right, you're effectively going to get something that is going to have a rho d phi dz d rho here, okay? You all with me? Now, listen. When I take a look at this, I'm going to get a 1 over rho term down here, right? Just listen. You all agree with that? The energy density is going to be a function of 1 over rho. What is the integral of 1 over rho d rho? Anybody? Natural log. Well, what happens when you go ahead and evaluate this? Remember, we're just talking about per meter energy density from an infinite line. Well, that would be something where I get the natural log of infinity divided by whatever the inner radius is. Do you all follow me in that? What's the log of infinity? Infinity 2, right? It's an infinite amount of energy density. And here's the one takeaway from this. Anytime you have an infinite amount of charge, or you have an infinite length current, the energy dense or current surface current, anytime it's an extent is infinite, the amount of energy is infinite per meter. You all follow me on that? You will not have that. So, a good question you should be thinking of is, well, if I know I got a wire, and I know what the internal inductance of that wire is per meter, that's true. Well, how do I get the external inductance? This is something you're going to get a little later, but it has to do with partial inductance. So now what we have to do is we need to know something about the closure of the path. And once we do that, then we can get an estimate for the H field or B field in the vicinity of that loop, and we can therefore estimate this. I'll talk about this more later. But y'all follow me, you can't assume an infinite wire, because if you do the energy density per meter is going to be infinite, that means the inductance is infinite. Well, there aren't no such things as infinitely long wires. So it all depends on the closure of the path. And by the way, if you have a wire in it, if you have something that's in the differential mode, current going down one way and back the other, the closer those two wires are to each other, the less the actual inductance per meter is, which is good if you want something to respond quickly. You want very low inductance. More coming up on this. So I just showed you how to calculate inductance for the classic example of the internal inductance of a wire. And I don't even know if he talks about partial inductance here. I know he's going to do it later, but I don't think he does. This will come later. I'll show this to you in EMAG 2 if you're taking it. And this is very interesting, but it's something I'm not going to get into right now because, frankly, I don't think we have time for it. Just remember what I told you. It's important and appreciate it. So next, well, if that's the self-inductance, what about mutual inductance? We're going to do flux now. And you can do self-inductance this way too, but I'm going to show you a trick. So if you want mutual inductance, in your own words, what's mutual inductance? You had something about this, I think, it's circles, did you? What is it? Yeah, turns ratio and transformers, but, you've heard the term mutual inductance, right?
Yes.
Very hesitant, yes. Maybe.
I don't remember. Maybe.
I'm not believing I did. He probably did, but he didn't go into it. Did he go through magnetic circuits in your circuits course? Did you ever?
If you mean circuits with inductors, then yes.
Did he talk about transformers?
You talking about, that's more in power.
You didn't have transformers in circuits?
No.
He did very
Oh,
briefly in like the last day of class.
Never mind.
Last 2
All right,
days.
I'm going to deal with it. I'll get to that later. Here's self-inductance. Here's the reason. If you have a current element, and I'll give you a classic example, I, and then you have a closed loop, all right? And you want the actual mutual inductance between these. This is mutual. Sometimes they call it L sub n, mutual inductance. First, I should define what it means. Well, technically, mutual inductance means this. If you have a gap here, plus to minus V, and I'm going to put a load here, R load here, I'll call this V2, and you take a look at mutual inductance and self-inductance. Let me do it with a magnetic circuit, the way they do it. You'll appreciate this more. So normally they do this. Now, this looks like a transformer if it had turns ratios, but technically this is a magnetically coupled circuit symbol. So if there's a voltage V1 here, and a current going into the dotted terminal, we'll talk about that in a bit. You had power. How many of you have had power? All right, then you know dotted terminals, I hope. You'll get this in a second. You'll figure it out. All right, and then you have another thing, as a dotted terminal here, that has some voltage across it, call this V2, and a current going into the dot here, call it I2. Here's the mathematical relationship. This would have to do with lumped elements. Remember? That's a lumped element, a transformer or a mutually coupled circuit. It would say that V1 here is equal to L1 times, and technically it's dI1 dt, plus M times, or the LM, I'll use LM, times dI2 dt. And V2 would be equal to, and here it's going to be the mutual Lm times di1 dt plus the actual self-inductance of the second circuit, L2 times di2 dt. That's what it technically means. Now usually, the time derivatives just become J omegas. All right? So, I mean, usually this, so you get this. You'll get V1 is equal to J omega, and then you'll have, first one is going to be L1 I1 plus Lm I2, because J omega is there, and you'll get V2 equals J omega, and it's going to be mutual Lm here times I1 plus L2 I2. And they write these in terms of a matrix form too. I'm just showing you. What it really means is the relationship between voltage and current on one side or the other side of what can be thought of as a transformer. It's a magnetically coupled circuit. With transformers, the actual, it's called a coupling coefficients becomes 1, and I don't want to go there. They're very efficient coupling power from the first to the second circuit. And really mutual inductance and the mutual inductance is equal to square root of Lm or square root of L1 and L2 for a strongly coupled circuit. But I don't want to go there. I'm just showing you what it means. Now I'm going to show you how I calculate it over here. Oh, you all with me? I'm trying to give you a little background. These guys that have power understand this. They've had it. Did you have power or no? Coming over here. More on this in a second. So back to this circuit. What I want to do is figure out the mutual inductance between these two circuits. The way to do it is start out by assuming I on the wire here. We'll assume it's infinite, okay? Now assume this is at a radius out here. Call it radius A. Call the width of this W and the height of this H. Only one turn. You all with me? After I assume I, what I need to do is calculate the B field here into the wire, right? I need to calculate that B field. And let me just say where I'm going with this. I didn't do this. From I, after we get I, we're going to get H. From H, we're going to get B. Once we get B, we're going to calculate something called the flux penetrating that loop. It'll be the integral of B dot ds over the surface. Finally, once I get this, I get the actual mutual inductance here by saying it's equal to the magnetic flux penetrating that second circuit divided by the current causing it. This is mutual inductance. You can actually use it for self-inductance. I won't have time to talk about that today, but are you with me? How many have seen this before? Anything like that? You have, Chase, or not?
Kind of.
You have? Where'd you see it?
My physics 2 professor in high school taught me, or added a lot of curriculum, and this is a little bit of what he added.
This is important. It's a neat calculation. Here, we're not talking about energy. We're talking about something that you'll hear a lot about, flux coupling. The amount of flux goes through it. If you've ever seen Back to the Future, that guy, frizzy-haired guy, says it's a flux capacitor. Really? Wow. They use a lot of these terms kind of loosely. Anyway, now we're going to calculate this. Okay. So I have I. So tell me at a given distance, rho away, what is the H? Anybody?
2 pi, or sorry, I over 2 pi rho.
Right. Now, oh boy, I'm going to sneeze in a second. I hate this feeling. All right. Well, how do we get B?
It's just B, yeah, it's
Just mu, right?
Okay.
So we got B now. I'm really flying here. All right? It's in the A phi direction. It'll become inconsequential in a second. You with me?
Mm-hmm.
Now we find the amount of flux that penetrates this loop. By the way, this is going to be per turn. Usually there's more than one turn. So how do we get the amount of flux?
Integral of B dot ds.
That's right. Integral has to be a double. Integral of B, which is mu I over 2 pi rho A phi dot, and here it's going to be d rho dz, right? Can't be in the A phi direction. Remember, the differential surface it's got magnitude, and that's just d rho dz. That's this, but it has a direction also. It's A phi. What? You had that cockeyed look like I don't quite get it. You with me on
I
this?
got it now, yeah.
All right, now, where are the limits for rho? This is A phi, by the way. What are the limits for rho? Just like
Would it be rho to W or rho to
from
rho
A
plus?
to A plus W.
Yeah,
All right.
A to A plus W. Plus W.
A to A plus W. What about Z?
Oh, I have a
0 to H.
Is there supposed to be an extra row because of it's cylindrical, or is that only?
No. If we're going this way, it was an azimuth integration. We have rho d phi.
Oh, the phi term has the. Okay, that makes sense.
This is the rho d phi would be the wiper arm going. Here we're just going up and out. So it's d rho dz. And where does z go from?
0 to H.
Yeah, start at 0, go to h. You could say it at some k, and then k plus h, but the k's are going to cancel. So just go from 0 to h. All right, what is that going to be? I'll put it over here. Take a look at this. Let's just talk our way through this. Y'all agree A phi dot A phi is one class?
Yes.
All right.
Yep.
Now, keep looking. What happens when I'm going to have a mu I over 2 pi, correct?
Yep.
Okay. Now, integrate d rho over rho.
Natural.
Natural log from
A plus W over
A. That's right. Over A. And you can make that 1 plus W over A if you want, but it doesn't matter. It's the same value. And what about the height integral? dz times h. So, and that's the magnetic flux that penetrates that loop per one turn. Next question, what if I have 2 turns? It's not a trick question. 2 turns,
And it would be 2 times.
twice. 3 turns, 3 times. N turns, N times. So normally what you'll see is an N come out here. And this typically, the symbol they use is this, and that means just flux coupled, or coupling, i.e. the capacitor from Back to the Future, the flux linkage or whatever it was, flux capacitor. So I don't know where you got that, but it's
It's lambda in the book.
It's the lambda.
it's right there.
Yeah.
You see it?
Yep.
Okay. Now, once we have that, look up here. Inductance right here is equal to that flux coupled divided by current, or we can say inductance itself is this divided by current. So the current goes away and I have mu times number of turns times h over 2 pi times natural log of A plus W over A. And that's called the self-inductance of a single turn, of an in-turn coil. And that's used all the time. You with me with that, class? I hope you are. Wasn't meant to be hard, but I'm going to show you. It's not. If you think about this with inductance, probably the single best thing for me to do is give you some problems to work with this. And you'll see them. And then once you see it, it becomes, oh, that wasn't that hard at all. But the trick is this, you got to spend time doing this stuff, because some of this stuff gets a little confusing if you don't. Now, my next thing I'm going to do is magnetic circuits. I'm trying to lump these things. I know this seems like a lot coming at you, but do you all follow me on this? It's either one of 2 ways. If it's either you're going to get the energy or you're gonna get the flux. Now we can do the first problem, instead of calculating the actual energy density and doing that, we can calculate the flux length per per unit current. I don't want to even do that right now because it's going to take a little too long, but energy is the classical way to do it for self-inductance internally. Did you have a question, anybody? Now for magnetic circuits.
I do have a question. Is that mu r times mu naught?
Absolutely.
Okay.
Mu is just the relative permeability times mu naught, and mu naught is 4 pi times 10 to the minus 7, and it would be, in this case, Henry's per meter. That's all it is. With me? All right. Now for magnetic circuits. I'm going to go over. Because I'm going to give you problems with this, I promise you. And you got the solutions, but make sure you keep up with this, because some of this it'll get a little bit hairy and confusing if you're not keeping up with it. And I mean, magnetic stuff it's very, very useful, and there's not a whole lot of people who got a good handle on it. As a matter of fact, you'd be surprised when you get out in the real world how many people have these great gaps in understanding. They'll make assumptions. I mean, y'all seen things like speakers are 8 ohm or coax cable is 50 or something like that. They'll assume if they just measure that with DC meters, surely that's it. It has nothing to do with that. And you'll learn about all that later, but I'm going to say there's a lot of people that have a vast gap in their knowledge base, and they're getting out in the technical world, and things go wrong in a hurry. All right, next thing we're going to talk about are magnetic circuits. Now, how many weeks do we have left? 3? All right, we're going to make it. We're going to get through chapter 5. Don't worry. I will get you there, I promise. All right, so for magnetic circuits, what is a magnetic circuit? It's really equivalent to an electrical circuit, but instead of current, you're going to have flux and all these things. So think about an electric circuit. For an electric circuit, you're going to have resistances, you're going to have a voltage. I'm making it as simple as possible. There's some voltage. If this is some R1, R2, that voltage induces a current. And y'all follow me with this, right? Okay. Magnetic circuits, the simplest magnetic circuit, is take a rectangular bar like this. I'm going to make it closed. And the thing has some dimensionality like this. Alright? And kind of deal here. Y'all follow me? Now, if we have N turns, let's show N turns here with a current I, and I'll take the cross section out of it. I'm going to do it like this. We're going to look straight down. I'm not trying to get 3D projection here. We have something where this is going to be A. I'm going to make this square. This is A that has a cross-sectional area here equal to A, right? In other words, capital A in that case. And now I'm going to have N turns of wire wrapped around it. And each one of these turns is going to have a current I going in. Here I'm even going to dot this terminal so you'll understand. Still follow me? We have N turns. Follow me? Now, what is going to happen is that coil of wire is going to cause a flux to flow this way. There'll be a magnetic flux. Can y'all follow me? We're going to calculate this. With me on this, class? Now, first of all, you get something called the EMAG. So, like over here, you had a voltage, right? Now for a magnetic circuit, I'm going to draw it right here, parallels this. Matter of fact, let me get rid of that drawing so I can do it this way. Let me finish this train of thought. instead of a voltage, we're going to have something that's akin to a voltage. It's a magnetomotive force, and MMF is simply given as the number of turns times I. Now, that dot shows you the polarity of the direction of current. Y'all have right hands. You take your right hand, grab the coil of wire such that your index finger points in the direction that the current's flowing. You see your thumb? That gives you the positive sense of the actual magnetomotive force, or the direction positive flux will go. So it's like this. This is MMF. Next, remember over here, if you wanted the resistance of a long bar, resistance was what? Length over cross-sectional area divided by sigma. Do you all remember that from resistance class? Over here, if we just have this, and I'm going to say that the total length of this thing is really equal to 4A. It goes this way, this way, this way, and this way, all of length A. 4A is the total length. Well, now you get something that's called reluctance. And this is the magnetic reluctance. And it's proportional to length. It's inversely proportional to mu, which is mu relative mu naught, and inversely proportional to cross-sectional area. For the one I drew there, it's going to be 4A is the length over mu. Cross-sectional area would be the reluctance, like resistance. Y'all follow me? It's just like resistance. Here I have two resistors. Maybe I should just have one, like so. And you can see the exact parallels. You all with me? Now over here we have a current I. What is I equal to? Voltage divided by resistance for an electric circuit, right? Well, here we have something akin to current. It's magnetic flux. It's just like current. And it's equal to the MMF, or I'll just put it NI, the MMF divided by the reluctance, RL. Can you all follow me on that? That's the reluctance. Now, if you have that, that's like current. How do you get current density? I know you're looking for the bus, but I'm going to finish this slide. Just give me 1 second. How do you get, if you know like the I and I want J, what do you always do? Divide by cross-sectional area, remember? So if you take the magnetic flux and divide it by the cross-sectional area, you get the B field. Alright, and that's like the current density. You with me on this? Now, all that said, here's something else. If I've got this, and I know the flux, it's Ni divided by the reluctance, I can get the inductance of this. You know how? I can say the self-inductance of this thing, right here, is just the total flux Ni, right? Or sorry, it's equal to the total flux, which is going to be Ni over the reluctance. Here's what I'm talking about. I can say this is the total flux times the number of turns divided by I. Well, the magnetic, I'll put N first. The magnetic flux right there is Ni divided by the reluctance. So it's N times Ni divided by the reluctance divided by I, or it's really proportional to N squared divided by the reluctance. Y'all follow me in that? And that would be the total series reluctance. I'm going to give you some problems. I've kept you, I know, I've kept you about 3 minutes extra, but I'm going to give you some problems in this, and you're going to see this magnetic circuit stuff is going to be trivial. Then we're going to get to the pulling power of the bar magnet stuff next class, and I'm also going to do batteries, okay? I apologize for keeping you late, and I apologize for not posting on. Go ahead.
I got one question. What do those terms say with the reluctance? Is that just L over
Mu.
That's
My
mu.
mu A.
Okay.
It should be in the book.
It's mu. Is it
Mu.
mu instead
Like
of sigma?
Mu relative, right? No, that's electric.
Yeah.
That's
you're
right. I'm trying to just show you parallels. I hope it helps. Okay, guys.
Mu.
I'll get your, I'm sorry, I'll bring your quiz back. It's probably in my office. If you want to walk with me, I'll get it for you. You have to go.
Quiz Friday?
It's Wednesday, right? I mean, this coming up lecture is Wednesday. Quiz is Friday. Wednesday's coming up, right?
Yes.
I didn't miss that then.
Today's Monday.
Fine, man, I don't know